Hey everyone, let's get started. So last week I promised that I would give you a little refresher on assembly language and on RISC-V in particular, and so we'll do that today. Hopefully I'll be able to get through all that material today so we can get started on the lab on Wednesday. So last time I was talking about the RISC philosophy for designing instruction sets, and the idea is that RISC has a RISC instruction sets, which are used in ARM and RISC-V and MIPS, Spark, and a lot of other more modern architectures, are designed to have relatively small instruction sets, meaning that the number of instructions that you can execute is the repertoire size, the menu size, the set of instructions is fairly small because each instruction just does a little bit of work. And so when you execute the program, you have to execute a whole lot of instructions. The problem with that is that that's great for the compiler, and it's also good for the performance of the hardware because you can design a very fast pipeline for those instructions. But it's horrible if you have to actually write code because there's a lot of typing involved, right? There's a lot of instructions in your program. So that's one of the it's one of the problems with RISC. So it wasn't designed to be written in assembly language, but we're going to do a little bit of that just to develop some test code that we can use when we design the processor, so we can run the code on top of the processor. And as you debug the hardware, you'll have an expectation of what's showing up in the registers as the program runs, right? Yes. They're on the website. I was running a little late adding those, but they're on there now. If you go to Blackboard, they're under Downloads, under Lecture Slides. I should probably have a different category for Lecture Slides, but they're under Downloads. Okay. Okay, so the RISC-V instruction set is a modular instruction set, meaning that it has a base set of instructions and extensions, which are optional. So this way you can design a very lightweight RISC processor that only supports the base instruction set and some of the extensions, or you can create a heavier weight processor that has more features, supports more instructions. So the base instruction set is called RV32I, which is the base 32-bit instruction set. It contains the main type of instructions you learned about in 212, which is the arithmetic, comparison, shift, logical, right? Logical basically number crunching, data crunching, calculation instructions. Those are the arithmetic. And then the load and store instructions, which access external memory or I/O, and then the control flow instructions, which are branch and jump. Then there's 64-bit instructions, integer instructions that sit on top of that. So the base instruction set in RISC-V only has 47 instructions, and we'll only be implementing a subset of those in this class. Yes? It's instruction set architecture. So that's everything you need to know to write assembly code for the processor or to write a compiler that generates assembly code for the processor. It's everything. It's the interface to the hardware, right? So that's going to be public. That's public knowledge. That's going to be published in books and stuff. But underneath the hood, how the processor how it actually executes those instructions, that's always going to be a trade secret. Okay, that's the part that we're going to design in this class, the underlying hardware. But you have to understand how those instructions work in order to design the underlying hardware. Okay, so the base instruction set's only 47 instructions. The 64-bit adds another 14. And then there's the M module, which adds integer multiplication and division. We're actually going to have multiplication, but we're not going to put in the division. So we're only going to implement part of the base instruction set and part of the M instruction set. And then you have features like atomic memory operations, which you need if you have a multi-core processor. Then you have single and double precision floating point. They have a quad precision floating point, Q. Then they have a set of compressed instructions, which are only 16-bit instructions, which are analogous to ARM's thumb instruction set. That's for like where you're very memory constrained. Then they have a vector instruction. You'll notice that the vector instructions that's kind of wild. That's 186 instructions. It's a huge set of instructions, but those are there to support machine learning and scientific computing and stuff like that. That would be a cool thing to add to this class, is some vector instructions, so we could start doing some higher performance processing. Then they have hypervisor support, and then they have a set of they have a couple Z sets of sub-extensions and that add stuff like niche stuff like cryptography and adding cache hints and that kind of stuff. So currently those are all the ratified sets of instructions, and you can see that each category is fairly small. So in comparison to MIPS, RISC was designed to be very similar. They both have 32 general purpose registers. In machine language, those registers are referred to as an address, a 5-bit address. So you put 0 to 31 in there. So you'll see an address associated with a register, which seems kind of weird because it's a register number, but it's the address in the register file. And then in assembly language, in MIPS, you use X0 to X31. And then they have some other names for each of those registers too. But if you just want to refer to them as an actual register number, as an architectural register number, it's X0 to X31. And then remember, MIPS was $0 to $31, so that's a little different. And then, as I mentioned, there's alternative names there as well that you may use. In this class, half the class will use the X registers, and the other half will use these, S0 to S11, T0 to T6, A0 to A7. In fact, some of the system calls that we use are using this convention, so you'll probably, it's best to use this convention. But I'll show you how to look those up in RARs in a minute. And then register 0 is always 0. And in the assembly language, you can actually type out 0, and that just refers to register 0. It's a good way to, for example, if you want to move, not really move, but copy. If you want to copy the contents of one register into another, then you can add 0 to it and write the result to another register. And then it also supports immediate operands, which are used for constants in your code, for incrementing a loop counter, or whenever you need a constant in your code. That's kind of baked in. Okay, so in order to give you a refresher course on assembly language, the way I have structured this is to show you what I think is most annoying about assembly language and present it from that perspective. Things that make why is assembly language programming difficult for a human being? So I'm going to present to you my 5 or 6 different reasons why this is difficult. So for one, a computer in the machine language can only perform operations on 2 inputs at a time. But if you look in like your high-level code, your C code, you will often have lines of code that have multiple inputs, right? So for example, in the slide there, I've got f equals g plus h minus I plus j. There's effectively, that is a function. You can consider f to be a function that calculates an output based on 4 inputs. But the problem is that in assembly language, you only get 2 inputs. So you have to decompose a line of code like that into multiple instructions where you're having to explicitly store intermediate results to decompose the more complex expression into simpler expressions, right? And then the other problem, as I mentioned last week, remember that MIPS is a load store architecture. You can only actually operate on registers, not directly on variables. So I've got, F, G, H, I, and J are all variables, but I have to, in terms of them being variables, that's referring to them in memory. So you're assuming that when you assemble this, there's a symbol table that associates each one of these variable names with a memory address, right? And so you have to then load the value from that memory address into a register before you can do anything to it, and then you have to store the result back, right? So the problem with this is I have to allocate registers manually, which is awful. So I have to decide which registers I'm going to associate with each one of those variables, and then the association is formally baked into the code with the load and store instruction. So for example, if I load G into register S1, I am now associating variable G with register S1. That S1 is going to be a live register for as long as it's live in the code, meaning that I can recycle register S1 when I'm done with it, but there's no obvious place in the assembly code where I'm done with it. It's unclear where that is. It's basically from the program, inside the programmer's brain, you decide when you don't need that anymore, and then you can reallocate register S1. So registers are a constrained resource, so you have to recycle them. And you have to decide how you want to use them, and you have to remember which register is associated with what variable, and how long each register is live for before you know when you can recycle it. So in this case, I load G into S1, H into S2, I into S3, and J into S4, and then I have to take that expression and basically count the number of operators in there. So I've got 2 adds and 1 subtract, and so I have to do 2 adds and 1 subtract. That's going to take 3 instructions. 2 add instructions and 1 subtract instruction. And the G plus H would be, I have to allocate another register to store that sub-expression G plus H into another register as a temporary value. And likewise, I have to store the result of I plus J into another register as a temporary variable. And again, choosing which register I want to use for that. And then finally, you have to go back and remember which 2 temporary registers you used for those 2 sub-expressions, and then add them together for the final add. So what I did was I added S1 and S2. I put that into T0. Now you can see here where I'm using the register symbols to my advantage. S is like a promoted value, like I'm using the S register to represent a variable, like an important value, whereas the T's are temporary values. And the only real difference between those is like how long each lasts. Like usually, like we can assume that I might want to keep, like G, H, I, and J might be alive for longer, so I'll make them S registers, but this is all arbitrary. You know, this is all up to you as a programmer. So anyway, I'm going to load G, H, I, and J into registers S1 through 4. Then I'll have the 2 add instructions and 1 subtract. Oh, I'm sorry. It's actually a subtract is the last operation I do, not an add. So the G plus H are in register T0 because that T0 is my destination for the add. I plus J is in T1. Then I subtract T0 from T1. I put the result into S0. And then I store S0 back to F, right? Now notice in this case that all of these instructions have a destination that comes first, which is meant to represent the L value in a typical high-level language. So if I say, you know, A equals B plus C, A is the L value, that's the destination, that's what I'm writing, that's the output, and the assembly language is structured in the same order, except for the store. Because when I store, I'm storing to F. F is the destination, and yet F is the second operand. So that's like, I don't know why F should come first, right? It should be store word F comma S0. But like some idiot designed that, basically. Like it doesn't make any sense, right? It's inconsistent, right? So you just have to keep that in mind. Some assembly languages actually do reverses. I think TI's, Texas Instruments, has one there where their stores, they swap it. Okay, of course, in their case, all the destinations are last, actually. So they're, but anyway. Okay, so here's another example where this gets a little bit more complicated. So I have an expression A equals B plus C times D plus B. And so in this case, the order of operations are defined through, you know, the parentheses and also the classical order of operations you get mathematically. In this case, I want to do B plus C first, so I have to load B, load C, and it registers T0, T1, and then I add those together. I put the result into T2. Now notice I'm using some comments. So the hash mark there represents a comment in assembly. And so I'm trying to help myself out a little bit to remind me what's going on in here. So B goes into T0, C is in T1, B plus C is in T2. Okay, and then I load D into T3. D is the next value I need. I need to multiply D by B plus C. B plus C is in T2. So I do that. So T2 times T3. Again, T2 is my B plus C. T3 is my D. I multiply those. I put the result into T0. And now I have to add B, right? But the problem is I have a bug now. This is a problem. Because what happened was, if you look at that code, B was used twice. B is referenced twice. B is referenced here, and B is referenced here. So when I loaded B, I initially loaded into T0. But then when I calculated this sub-expression, B plus C times D, I recycled T0 because I assumed I was done with it. Because why? Well, it makes sense. I added B. I was done with it, right? But the problem is that now I have overwritten B's gone. T0 has been recycled a little too early because I need it here to add to the end here, to the last add, right? So of course I could reload B if I wanted to, but it would be preferable to keep B alive in register T0 longer so I don't have to put that extra load instruction in there to redundantly load it twice. You see what I mean? Because that reduces, that way I can keep the number of instructions to be one less, right? So this multiply instruction using T0 as the destination was a poor choice. I jumped the gun there when I was recycling my T0 register. I recycled it too early because T0 was still technically alive because I still needed B. Yes?
When you make T0 the destination register, that automatically, it doesn't do any checks, it just rewrites it.
Yeah. It just overwrites it and then B is gone. It's not in the CPU anymore. It's still in memory, but it's not in the CPU anymore. Okay, so so my point of all that is you have to allocate registers manually, and that's a pain. And it is a common way to introduce bugs in your program if you recycle registers too early. That's the point there. The other thing that I really hate about assembly language is that in high-level language, the way that you structure an if construct, you'll say if, for example, if condition, and then you have the true part, and then you have else, and then you have the else part, right? So there's the true part and the else part. The code you want to execute if the condition is true, the code you want to execute if the condition is false, right? And before all that, you have to test the condition, right? Now, in assembly language, the way that you do that is through a branch instruction. Branches and jumps are basically the way that you implement if statements and loops, right? The difference is that branches are conditional and jumps are unconditional. Okay? So branches, because they're conditional, typically you'll use those to implement an if statement, right? Or a loop continuance condition, right? The problem is that if the branch is evaluated to be true, the way a branch instruction works is you test a condition, and if it's true, you change control. You're gone. You leave this part of the code, right? You jump to another instruction. You don't go to what's called the fall through instruction, which is the instruction that appears under the branch. That's the fall through, right? The problem is that is not how high-level code works. The way high-level code works is you say if condition, then fall through, meaning that if it's true, you fall through the if statement. But that is not how assembly works. The way assembly works is if the condition is true, you don't go to the fall through, you go to another spot in the code, right? Which means that if you want to structure the assembly code in a way that matches the order of an if, then, else statement, you have to logically negate the condition, meaning that you test the opposite of what you would be testing in the if statement in your high-level code, because if that condition is false, meaning the high-level condition is true, then you go to the then part, which appears after the branch and after the if statement in the code, right? So you have to think about this. You have to say if A is less than B, oh, no. You have to check to see if A is greater than or equal to B in the assembly code, which is the opposite. It's the logical negation of A less than B. So I have to look, in this case, you can see I loaded A and B, and then I used a BGE instruction, branch of greater than or equal to, just simply because greater than equal to is the opposite of less than. And it said less than in the high-level code that I'm translating, right? So I have to do this logical negation. I mean, you don't have to do it this way. I mean, this isn't the only way to write assembly code. The other way to do it is you could test to see if A is less than B, and then you can simply then have your then part below the else part, right? Right, that's an option too, but I don't think anyone writes code that way. I think they generally do it this way, right? Where they negate the branch as compared to the high-level if condition, right? Does that make sense? This is all up to your own preference. I'm just showing you the way I do it. So if A is less than B, as in my C code, the assembly code will say if A is greater than or equal to B, then go to the else. So it says branch if greater than or equal, S1, S2, which corresponds to A, B. Now, the other thing you could do is you could have swapped A and B here. You could have said branch if less than and then just swapped A and B in the arguments list too for the branch instruction. That's another option. But either way, you have to make some kind of modification to your branch in order to get you into the then part as opposed to the else part, right? And then, so basically here, if A is greater than or equal to B, I go to the else. Otherwise, I fall through, meaning I just continue to go whatever instruction was under the branch, in which case I do the then part where I load a 1 into register T0 and then store it back to A. right? Meaning I set 1 into A, and then I branch to exit. Notice that, yeah, I forgot about this. I have to correct something here. So in MIPS, it was jump. Jumps were unconditional. RISC-V has a weird thing where they have unconditional branches, so it's B exit, right? That's a little confusing because I just said that branches are always conditional and jumps are unconditional. There is an unconditional branch in RISC-V. I forgot. I always have to correct myself because some of them, I'm still not entirely used to RISC-V as compared to MIPS. But yeah, there's a branch exit in this case. After I get done with the then part, I skip the else part. So I go to exit, which is the first instruction after the else part. And in the else part, I load 2 into T0 and store that to B, right? Now, you might say, why do you have to do a load? What is that, LI? LI is load immediate, basically puts a constant into a register, and then you have to store it. Do you really need 2 instructions just to say A equals 1? Really? I mean, A equals 1 is so fundamental. That seems so simple in C. Why do you need 2 separate instructions? Well, again, it's one of the annoyances of using a RISC. You can't just store an immediate, for instance. You can't just say store 1 to B, right? You have to figure out what register you want to recycle. In this case, I chose C0. I'm going to recycle. Hopefully, that wasn't used for anything at this point in the code, because I just killed it if it was. I'm going to put a constant 1 in there, and then I'm going to store it to A, right? So just saying A equals 1, B equals 1 requires 2 instructions because of the annoyances of RISC. Okay, so here is another one, and this one really gets me. So if you have a for loop like this, you say for I equals 0, I less than 100, I plus plus, and then you just have an array access. You say vals of I, right? You would think that there would be a load instruction for vals that would allow me to incorporate I into the load instruction as a variable index or as a variable offset into the array. You would think, right? I mentioned this last week. This is the one that really annoys me. Now, I know the reason they did this was because this is a trade-off, basically, because in order for them to have hardware indexing for arrays, they would have to add another adder inside the data path of the CPU, which would cost hardware, and it would only be used in a very small portion of the instructions, just whatever loads are doing array indexing, right? So this was a deliberate trade-off, but for you, it makes it a little bit more difficult to write code. Although in this class, though, to be fair, we're not even doing loads and stores, so this doesn't really relate too much to this class. But just I wanted to mention, you might remember, in this case, I have to load vals. I have to load the address of vals into a register, in this case, x2. Notice I'm going back to the X version of the registers. And then every time I access vals, I basically have to add, well, in this case, I'm adding 4 to that base address x2 to vals, okay? And then, and that's only because I'm walking through it sequentially. And then I have a separate counter here for x1 that keeps track of I. So in this case, I, in the C code, I is being used as the index and as the loop counter, whereas in the assembly code, I have to have 2 different ways to implement those. I have x1 as the loop counter, and I'm using x2 to keep track of where I am in the vals array. So that's kind of annoying. And this is just another example of this. So in this case, I have I twice. I have destination I and source I. So I have to keep track of 2 pointers for destination and source. Notice I have T1 and T2. I use this LA instruction, load address, in order to establish those. And then I'm using an add, let's see, where am I doing that? Oh, okay, so in this case, this is a little different. Actually, I approach this a little different. In this case, I have T0 is my I, right? So T0 is added to as the last thing I do in the loop body. And then I use T0 with this branch if greater than or equal to control when I exit the loop, right? So the branch instruction is using T0, which is implementing this condition, this continuance condition. And I've got the increment at the bottom of the loop, right? But in order to index my arrays, I'm actually having to shift T0 by 2 bits to the left. Why am I doing that? Because T0 is incrementing by 1 each time through the loop. But in order to use it to calculate addresses, I have to not add 1, I have to add the size of each element in the array, which is actually 4, assuming that this is 32-bit values here. I don't show the declaration. Oh, I do. Integer, source, dest. Yeah. Assuming it's a integer on a 32-bit machine, right? So I take T0 and I shift it by 2 bits to the left simply to multiply it by 4, So this adjusts the, and I store that into T3, and then I add T3 to my base addresses T1 and T2 to calculate the effective address of T4 and T5, which are used for source and destination, right? So the point of this, the point I'm trying to make here is that I had to jump through some hoops here in order to have a loop counter that counts up by 1 each time. And I had to then modify that loop counter to prepare it to be added to base addresses in order to calculate where I am in the array, as opposed to just having an index register in the load instruction where I could just tell it to index, right? So, you know, like I mentioned, instruction sets from the 60s had indexes in load instructions. From the 60s, the IBM mainframe had an index register in its load and store. But yet they didn't put it in here because they wanted each one of these instructions to be as simple as possible so they can achieve maximum throughput and minimal hardware usage, right, for this thing. It was a conscious decision. But it just makes life really miserable for an assembly language programmer. The other thing that I really hate, big pet peeve, is you can't do a comparison to a constant. So you just can't say branch if x1 is less than 0, branch. You can't. You have to preload a register with the one thing you want to compare it to and then do the branch instruction. So you can't say if a is less than 0 in one instruction. It takes 2 instructions at a minimum. Yes?
Technically, for 0, use just the 0 register.
Yes, that's a good point. That's true. That's an exception. Yeah, that's right, for 0. But if it was another value besides 0, then you have to preload it. Yep. Okay. Let's see. All right. So in this class, we're trying to, the goal here is, even though RISC-V is a small instruction set, or at least the base instruction set is small, we're going to whittle it down even further into a set of basically the most commonly used instructions. And the goal is that if you compile code from GCC or Clang into RISC-V, chances are that your processor will still be able to execute it because we're targeting the most commonly used instructions. Now, if we wanted to boot Linux on your RISC-V processor, we would have to implement additional instructions that Linux assumes that you have for basically operating system services, specifically the memory management unit related instructions. So that's an option. I think there's only 4 or 5 of them that we could put in here. Of course, we'd also have to be able to implement some interrupts too. We'd have to have interrupt support. But there's a few things we could add in theory to your CPU to make it compatible with Linux. But right now, we're just assuming that we're going to write bare metal code. No operating system. You're just writing code. It's going to run directly on the processor. Right? And so we've got, as I mentioned, arithmetic, logical shift, and comparison. These are 3 register instructions, so they're the so-called R-type instructions. Basically, 2 source registers, 1 destination. These are the number crunching. Then there's the 2 register plus immediate. So 2 register meaning source and destination register, as well as an immediate constant. Then we've got some branches, some jumps, and then loads and stores we're actually not going to do. I don't think we're going to do. It's one thing I want to add, but we traditionally don't add loads and stores. And then there's some coprocessor instructions that are a little bit obscure in RISC-V. That's the CSRRW instruction. But someone would probably not guess that we would target that instruction because that's a kind of like I said, it's obscure. But we're using it because we're going to use it as a mechanism to get data into the CPU from the switches on the FPGA board and also get data out to the hex displays. So we're using these as our I/O instructions, okay? Because we don't have loads and stores which are needed for memory mapped I/O, which is how you normally do I/O. Okay. Let's see. This is another example. So you'll notice here, I think that, I mentioned we're not going to do a lot with loads and stores and load address, but notice here we have, there's a .data and .text. These are assembler directives. So this basically just allows the assembler to know what section of the code to put each of these things in. So the .text, I don't know why they call it text. Text means instructions or code. So that's going to be at a certain address. Your text will be in a certain address. Your data will be in a certain address. And so if you say .data and then you put a label called var, that var label will be registered in the symbol table as being the beginning of the data section. Whereas on anything under text, if you have a label under text, that label will have an address corresponding to something in the text section. So what I mean by, and you might say, what do you mean by symbol table? So in assembly language, the one conceit you have in assembly language that you don't have in machine language is you can use variables, symbols, basically. And it's the assembler that allocates those for you in the symbol table. So if you have a symbol, in this case, I've got a symbol called var, right? It's going to allocate var automatically. It's going to associate that to a memory address. Now you might say, well, wait a minute. If it can do that, why can't it allocate the registers for me too then? If it's allocating memory but not registers? Why? I don't know. I don't know why they don't do that. You have to allocate the registers, but it can magically allocate the RAM, the memory, right? So anyway, we've got var : .word, and so we have, in this case, .word is 32 bits, and then we have an array there, and we have it initialized with 1, 2, and 3, and then in this case, we're loading and doing some add and store, and I don't remember, oh, this is doing some stack operations, but yeah, whatever, not that important. Here's another example program, let's see, where we have some C code and a for loop, and you can see in this case, again, we've got a data section, and then I just basically set up the loop just like I did before. I'm going to skip through this. Okay, now one thing that we will do in this program in Lab 1 is we're going to want to do some console I/O, where the user types something in, just some real basic console I/O. In order to do that, you have to use a system call. And so system calls are services that are provided by the operating system, and we don't have an operating system, so there's a little kind of hardware abstraction layer that's built into RARs that implements system calls, some basic system calls. So these system calls are used for I/O. So typing things in, printing things out. They have some in there for playing notes, for playing like music and stuff like that. I've never seen anyone use that. They have some, and I think they even have some that'll do GUIs, like that'll pop up windows and that kind of stuff. So basically the way you use a system call is you look up the system call number in the help under RARs. I'll show you where to find that in a minute when I do the demo. You stick that into A7. So notice that down here, I load immediate 5 into A7. So that is going to, A7 is the address of the system call. It's the designator for the system call. So system call 5 is, I think, read integer. And then you just use the eCall instruction. In MIPS it was syscall, and RISC-V they changed it to eCall for some reason. Use the eCall instruction, and then that will block. That's a blocking call. That will stop your program cold until the user hits enter on the keyboard. And so the expectation is user types in a number, and then because it's a synchronous system call, once the user hits enter, it will return control back to your program, and when it does return control to your program, register A0 will contain the value they typed in. Okay, so in this case, I'm taking A0 and I'm accumulating it into register T0 and basically looping, right? Okay, so here's another list of instructions. So we've got our basic arithmetic logical bitwise logic, arithmetic bitwise logical. So there's add, subtract, and, or, and XOR. Notice that there's just add and subtract. There's no unsigned version of those like there is in MIPS, because MIPS has that weird thing that they expect you to trap on arithmetic overflows. There's no arithmetic overflow detection in RISC-V whatsoever. So if you add and you overflow, you're on your own. Software's got to detect it. There's no seg fault is going to happen. And then and, or, and XOR are bitwise logicals. You guys know what that is? Bitwise logicals? That's when you treat the two operand registers as an array of bits. And then you perform an operation between each corresponding pair of bits in the two registers, right? So there's two 32-bit registers, and you do 32 logical operations on each pair of bits, right? That's used for masking and extraction. Like if you have to extract a field out of a register, or you have to insert a value inside of bits 5 down to 7, or 5 down to 3, rather, inside of a register, you can use these arithmetic, they're called bit twiddling bit twiddling operations, bit level operations, right? That's what those are used for generally. And then there's shift instructions. This is also different from MIPS. In MIPS, the shift instructions assumed that you had a constant shift amount, which was specified in its own field. They allocated 5 bits inside the R-type instruction for the shift amount, which was insane because that was almost never used. That was an insane decision by Hennessy and Patterson back in 1980 when they came up with that one. I guess they expected people to be using a lot of constant shift instructions. So RISC-V gets rid of that. These shifts are variable shifts. So the shift amount is specified in the RS2 register. Oh, notice the terminology here too. RS1 and RS2 are the source registers and RD is the destination register, to keep that. And that's kept consistent in RISC-V, unlike MIPS where sometimes the destination was RT, depending on whether it's an R-type or an I-type instruction. So this is simplified. RS1, RS2 are sources, RD is destination. Then we have comparison instructions, which are basically instructions that perform a comparison between the contents of 2 registers and then write a 0 or 1 to the output register, depending on whether the comparison is true or false. And we had the same thing in MIPS. Notice that I think there's only less than, though, is the only comparison in here. Less than. And then there's a signed and an unsigned variant. So you have to be careful here because if you compare 2 values, the signed bit is either a signed bit or it's a very significant part of the value, right? Depending on if it's signed or unsigned. So you have to make sure that when you do a comparison, you consider the type, right? Just to give you a heads up, in Lab 1, we're using unsigned. And if you don't use the unsigned variant, the code, you'll have a bug. Okay? And then multiply. So whenever you multiply 2 numbers, yes?
Comparing a signed number with an unsigned number.
You'd probably require more than 1 instruction to do that, I would imagine. That's a good question, though. I don't know. Never had to do that. Yeah, you probably have to have some conditional code for that, I would assume. So for multiply, when you multiply 2 32-bit values, the product has to be 64 bits, or else you're very likely to overflow, right? Because multiplying 2 small numbers gives you a big number, right? So you have to have twice as many bits in the destination as the sources, right? The problem is that the instruction set inherently does not support data paths for that, for doubling size of operands, right? So the way they implement it in both ARM and MIPS, ARM and RISC-V, excuse me, is that they have 2 different multiply instructions depending on whether you want the upper or lower bits of the product. You guys with me? So if you want to multiply 2 32-bit numbers and you want all 64 bits of the output, you have to do 2 instructions. You have to execute 2 instructions, right? One of them will recover the lower bits of the product and the other one recovers the upper bits of the product. In MIPS, they didn't do it this way. They had 2 special coprocessor registers called high and low that would be written on a multiply or a divide. Okay? This is also important because we're going to need this in Lab 1 as well. Does that make sense? You guys with me? Okay. Okay, then we have our immediate versions where you just, same as the regular, but there's an I after the mnemonic and you have an immediate. And then the shift instructions also have an immediate version, but they're handled differently than MIPS. In MIPS, there was a shift amount field, whereas in the RISC-V, they just use the I-type instruction for the shift immediate, but hardly anyone, well, I shouldn't say that. We use shift immediate in this lab. Yeah, so I shouldn't say that. They're useful. But remember, there's shift I, SLLI, shift left logical immediate, shift right logical immediate, shift right arithmetic immediate. You guys remember shift instructions from, I'm assuming that you remember that from 212, so I'm blowing past that, okay. Okay, and then we have branches. So in MIPS, a lot of these branches were actually pseudo instructions, but RISC-V promoted these branches. All of these branches are real machine instructions. They're not pseudo instructions. So we have branch if equal, branch if not equal, branch if greater than equals 0, branch if greater than or equal to unsigned, branch less than, branch less than unsigned. Again, be careful with the signed and unsigned, depending on whether you're comparing signed or unsigned numbers. And then, as I mentioned earlier, and I forgot about this, I don't know why they changed this in RISC-V, but historically, a jump instruction was by definition the unconditional version of a branch, right? Likewise, branch was the conditional version of a jump. But for some reason, just to make things a little confusing, the unconditional jump is B instead of J, like it was in MIPS. So just be aware of that. And then there's a jump and link and a jump and link register. Jump and link is used to save the fall through, the address of the fall through instruction. So you can return, it provides a way to return back to where you jump from. So that's used for subroutine. That's how you implement any kind of function call. And then load and store. I mean, we're probably not going to have load and stores in the hardware, in our hardware design. I really want to add that though, because, well, it's a long story, but it would be nice to have load and store because it opens the door for us to be able to create a bus, to connect our CPU to a bus. So we can then connect to other things on the bus, a system on chip. So I removed those several years ago to simplify things, but I kind of regret it now. But yeah, those are load and stores, and typically in assembly code you use a label. You don't have to use a label. You can use base offset addressing in assembly if you want, but generally people use a label for that. Labels are little symbols you put with a colon after it in assembly code. Those can be used for data or text locations. And then there's this weird one called load upper immediate. This one always confuses students in this class. I always have a hard time explaining this one. So load upper immediate is a misnomer because it's not a load instruction in the sense that you're not accessing memory. A load upper immediate is where you take the immediate and you put it in the register. You might say, well, okay, but why not just use a load immediate? Why just not use an LI for that? Well, it's because registers are 32 bits here, right? Or 64 if we have a 64-bit version, right? But when you have an immediate, the immediate has to go inside the instruction, which is also 32 bits. So you don't have room to put a full 32-bit constant inside of an instruction because it would take up the whole instruction. So the compromise that's made is that the immediate field in RISC-V is only 12 bits. So the biggest number that you can have in an immediate instruction, including load immediate, is 0 to 4095 unsigned, or negative 2048 to positive 2047 signed, right? So a small number, basically. You can only put a small number in an immediate because you only have 12 bits of space. If you need more space, then you use a load upper immediate, which is an alternative instruction format called a U-type, which is not in MIPS. It's a new format for you guys. The U-type instruction actually has a 20-bit immediate. So if you want to put a big immediate inside of a register, in other words, what I'm talking about here is initializing a register, basically. If you want to initialize a register, you want to set a register to a starting point, an initial value. And if that value is larger than what can fit in 12 bits, then you have to use a load upper immediate to initialize the upper 20 bits of the register. And then sometimes then you will follow up with an add I instruction to merge in the lower 12 bits, right? So in other words, it takes two instructions to initialize a register to a 32-bit value. That's what the load upper immediate is for. It's for initializing the upper 20 bits of a register, right? And I think it's the only instruction in the U-type. So they have a whole instruction encoding type specifically for one instruction in RISC, which is crazy. Because remember in MIPS, they tried to get a lot of mileage out of a limited number of encoding formats. But in RISC, they just went crazy. And they decided they weren't going to do that anymore. Now there's all these different crazy ways to encode instructions. Okay, any questions so far? Okay, good. So the next topic is fixed point arithmetic. So we want to be able to do number crunching on values that are fractional. But we don't want to do floating point. Why? Because it would take too long to implement floating point. We don't have time. There's a lot of design work you need to put in to do floating point. You need to support additional, you need a floating point register file, and you need to have different encoding formats And then you have to put in the functional units. And the problem with functional units, the floating point functional units, is they're more than one cycle. So we're going to implement a pipeline CPU, and we're going to assume in our CPU that we have in-order completion, meaning that every instruction completes execution in the original program order. Because to do out-of-order completion is a little bit more advanced. It requires more logic and more engineering, right? So the problem is that when we're going to do integer instructions, because we can do them in one cycle, all integer operations can be done in one cycle on the FPGA. If you want to support floating point, now you have to have a functional unit that takes up to 14 cycles to complete. You guys know why? You remember this from 212? So floating point requires a lot of steps, right? Like if you add two floating point numbers, you got to look at their exponents. You got to find out which one is the bigger exponent. Then you got to go to the one that's the smaller exponent. You have to denormalize it. You have to shift it so you can align the decimal points. Then you have to add. Then you have to round. Then you have to shift again potentially if the rounding actually shifted the bits up, right? And then you have to do another normalization step. So there's a lot of steps going on in floating point. You have to deal with the exponent field and the sign field and the mantissa field. And there's a lot of rounding and stuff that has to happen. Plus, there's also special values in floating point to represent things like not a number and infinity. And there's denormal support as well in there. So floating point is expensive in hardware. And for us, it creates a timing issue with regards to how we synchronize the flow of instructions through the system. So we're not going to do floating point. So what is our option? Our option is to use fixed point. Fixed point is when you have an integer, but in your brain, as you program it, you assume that the decimal point, and I shouldn't call it a decimal point, technically it's a radix point because it's in binary, but I still call it a decimal point, right? You assume the decimal point is somewhere other than on the rightmost side. In other words, what I'm trying to say is that you apply a scaling factor to the number, which is a power of 2, right? So, for example, if you apply a scaling factor of 2 to the negative second power, then any value in that register is actually that value, but divided by 4. Because it's been scaled. What that also means is that 2 of the bits on the right-hand side of the register are actually fractional bits, not whole bits. So what you're basically doing with fixed point is you're logically separating the value between whole bits and fractional bits. So you allocate bits to either be whole bits or fractional bits, right? Or they could all be fractional bits, right? Or they can all be whole bits, but scaled by something like, instead of by 1, you could scale them by 248 or something like that. The point is that you apply an implicit scaling factor. And generally, when you do this, you refer to these as, say, in this case, I have a 6-bit number, and I want 3 fractional bits. So I'll call it a 6-3 number, for instance. Now, that's not standardized, by the way. If you go into the Xilinx FPGA tools in the high-level synthesis, they actually have it set up to where you say total bits and whole bits, right? So they do it the other way. In this class, I use the convention total bits, comma, fractional bits. So a 6-3 number is 6 bits in total. The rightmost 3 are fractional, which means that the unit in the last place, which is the least significant bit, carries a significance of 2 to the negative third power, which basically means that the number in there is expressed in terms of eighths, essentially, right? So the scaling factor is 1/8, right? Because there's 3 fractional bits, that means that the least significant bit is 2 to the negative third power in terms of its significance, its weight, right? So when now you might say, well, wait, the advantage of that, by the way, is you can just use integer instructions and you can support fractional numbers, and it's free. Free fractional support, no floating point hardware necessary. So then you might say, well, wait a minute, then why doesn't anyone use, why are we using floating point then? What's the point? Why use floating point? Well, the problem is that fixed point has some downsides to it. The problem is that fixed point has a fixed range, dynamic range. The dynamic range is determined by the number of whole bits. So if you have a 6-3, meaning that I have 3 whole bits and 3 fractional bits, then my range is determined by the whole bits, which is essentially 0 to 7, right? 1, 1, 1, right? Or if it's unsigned, -4 to 3. So I can only go from -4 to 3, right? Make sense? And then my accuracy, which is the unit in the last place, is what I described earlier, 2 to the -3rd power, 1/8. So my resolution is 1/8. My range is -4 to +3 for this 3-bit whole number, 3 bits for whole number. So again, this is a 6-3. So I have an accuracy, which is determined by the number of fractional bits, 2 to the negative power of fractional bits. That's my resolution or accuracy. My range is determined by the number of whole bits, which is 2 to the number of the whole bits, or if it's unsigned. If it's signed, -2 raised to the number of whole bits minus 1 to 2 raised to the whole bits minus 1 minus 1. Right, for signed. Right? You guys with me? Now here's the other problem, though. This is the bigger problem with fixed point. With fixed point, your precision is data dependent. What is precision? Number of bits, right? So double precision, single precision, floating point, that's the number of bits that are in the mantissa, basically, right? The number of bits that are in the significand or the mantissa. The reason why that is the answer is because floating point numbers are normalized, right? They're expressed in scientific notation. So there's basically, it's always 1 point and then whatever the mantissa is, right? However, in fixed point, you can have a value that has leading zeros. If you have any leading zeros, like if the most significant bits are all 0, you're actually losing precision because you don't count those. Those are not significant digits, right? So if I have this number and I have 0.111, my first 1 bit is in bit position 2, which means I only have 3 bits of precision, right? You guys with me? So basically what it means is that depending on how big, what the magnitude of the value is going to determine my precision, which is why, for example, if you take a picture with a digital camera, it's using a fixed point system in there, which means that if you take a picture of a dark room and you lighten it in a photo editing software or something, it gets all weird and noisy and grainy. And you're like, what the heck? Why? This is a $1,000 iPhone. Why is it doing this? I don't get it. Why is there salt and pepper noise in it, right? Well, that's because those pixels, when captured by the image sensor, had a low absolute value and thus had a low precision, right? Whereas on the other hand, if you go outside and you take a picture of a very bright scene, you get a lot more dynamic range in those pixels because they're more intense. The light value is more intense, and thus you are actually getting a higher precision image in those pixels, right? So anyway, that's the problem with fixed point. That's why not everyone uses it. Yes?
So I had a question like, did you had any the fixed point representation? Like the problem is with the number of representation depends on the fixed bit, the upper part.
Mm-hmm.
The non-decimal point part.
The whole bits determine the range.
They are both bits, yes.
Right.
So
fractional bits are the resolution, but the precision is the number of bits starting with the first 1 bit from the left, right? The leading 1 bit, essentially.
Asking, is there any application that you saw which was for machine learning specific? So you have a third parameter that is scale-up factor.
Yes.
So basically, I'm saying is like, say your value is between -12 to -16. It's still 4 values, but it's scaled up to the.
Yeah, that's essentially floating point, because the scaling factor there is determining where, instead of fixing the decimal point, which is a fixed scaling factor, you're saying I have a variable scaling factor. That's equivalent to just having an exponent in a floating point, essentially. The exponent is the scaling factor in floating point.
So if I have to implement this like 6, 3, scaling factor, which might be 2, 3, and I will have some bits for that.
Yeah, you'd have to implement that in software, though, right? So all this stuff is in software that I'm talking about. We don't have hardware support for this.
So
right?
my question was, can FPGAs have this tendency?
Sure.
That can do that?
Yes, yeah. We're not going to. So RISC-V doesn't have any support for that in their instruction set, as far as I know. ARM actually has a way to automatically, they have ARM actually has some support for that because they have basically a fourth number you can do on an add instruction. Well, actually I take that back because I think they dropped that in ARM 64. That was in ARM 32. But anyway, my point is that yeah, we're assuming that you can do a scaling factor, but you have to implement it in software, right? And it's not part of Lab 1, so I'm not covering it here. But that is something you can do in software, sure. But you're basically creating software floating point if you're doing that. You know, it'd probably be. Well, it's possible, but it wouldn't. I'm not sure how you'd hook it into the RISC-V instruction set architecture, right? There's no like instruction support for that. But just in a bare FPGA design, sure, yeah, you could support it. Yeah. Yes.
I couldn't figure out what was the question.
Oh, he was asking about. He was saying that in order to avoid this problem of having the precision being data dependent, you know, and being reliant on how many leading zeros you have that are not significant digits. He said you can apply a scaling factor and tie that as a metadata along with the value, right? And what I was saying is that that's essentially what floating point is doing, right? Floating point does that in hardware, right? He was saying instead of using floating point, use kind of a hybrid scheme that's not fixed point, not floating point, somewhere in between where you have this scaling factor. And yeah, that's possible. But that's something that would be done in software, not in hardware. I mean, or you just go full floating point, in which case you get very good hardware support for it. Okay, so the problem, by the way, the reason why that's an issue is because in fixed point, when you add two fixed point numbers, you have to make sure their decimal points are aligned. So they have to be in exactly the same format. They have to have the same scaling factor, right? So that's what floating point does, is if you add two numbers with different exponents, they have different scaling factors, you have to denormalize one of the numbers in order to make them consistent on their scaling factor before you add them. And that's the whole reason why floating point add is so expensive, is because of that part, right? So, let's see, I already talked about all that, sorry. So yeah, in order to add or subtract, you have to have the same number of fractional bits, right? But the problem is when you multiply two fixed point numbers, the number of fractional bits grows in the product. So if I multiply two 6, 3 numbers, my product is going to be a 12-bit number with 6 bits of fractions, right? Because remember that from grade school, right? If you multiply 1.5 times 1.5, it's 2.25. The 1.5 and the 1.5 have one fractional digit. The product had 2 fractional digits. So whenever you multiply, you add fractional digits, which is significant for this lab. So specifically, what we're going to do in this lab, I'll talk a little bit in more detail here. So the input for this lab is going to be the switches on the FPGA board, and there are 18 of them. Ideally, there would be 32, but there's not. And the next board that we buy, because they're discontinuing this board, will have even less. Because it's really expensive to put 18 switches on a board, it turns out, because that takes a lot of manual labor. And you have to get a lot of switches. So there's only 18 switches. So what we're going to do is assume that the number you put on the switches are the whole bits. Meaning that then we're going to add 14 fractional bits. And why are we going to add 14 fractional bits? Because we want to calculate the square root of an integer. But square roots of integers are often fractional numbers, right? Like the square root of 5 or 2 or 10, right? Anything that's not a perfect square is going to have a fractional square root. So we're going to put the integer in on the boards, 18 bits, and then we're going to calculate the square root, and then we're going to calculate it as a fractional number fixed point, right? So the data representation in your code should be 18 whole bits, 14 fractional bits, right? 18 whole, so it's a 32-bit number in total, 32 bits in total, but 14 of those are fractional, and 18 of those are whole, right? And again, this is determined because of the board. This decision was made because of what's on the board. Okay? Now, when we do the square root program, part of the algorithm we're going to use a binary search algorithm. And even if you use something like Newton's method or other methods, we have to square, at some point we have to square the number, right? So if you have a 32-bit with 14 fractional bits and you square it, you're going to get 64 bits on the output, and 28 fractional bits, right? Because remember, 14 fractional times 14 fractional is 28 fractional, and the total number of bits is 64. So you're going to have 1814, 1814, you multiply those. So this is just a 32-bit number, and we're going to use a standard RISC-V multiply instruction. Well, actually, multiply high and multiply. Remember, you have to use 2 multiplies to recover all 64 bits of the product in RISC-V because that's a limitation of the architecture, right? And you're going to get a 64-bit result. That 64-bit result will be split into 2 32-bit numbers. The upper 32 bits will all be whole bits, but the lower 32-bit numbers will just have 4 whole bits and 28 fractional bits. Why? Because again, there's 28 fractional bits. There's only 4 left over in that lower register. The upper register will be all whole bits, right? So what do you do after you multiply and we have double the number of fractional bits? Well, we don't want to keep 28 fractional bits. We need to get it back down to 14 fractional bits so we can proceed with our iterative algorithm. So to do that, you simply just shift. You shift 14 bits to the right, which knocks off the lower 14 bits and effectively rounds down. It rounds down to the nearest, 2 to the negative 14th power, right? Which is 1 over 16,384. So we're going to round down to the nearest 1 over 16,384. Okay? But here's the problem. You have to shift the whole 64-bit number, and there's no 64-bit shift in RISC-V. So how do you shift a 64-bit number when there's no 64-bit shift? Well, like is usually the case, if you don't have a single hardware instruction to accomplish your goal, you have to perform it in multiple instructions, right? That's how assembly works. The whole idea is that assembly instructions are so cheap because they're so simple, we can easily afford to generate a whole bunch of them to perform something like this. So the way you do it is you take the lower 32 bits, you just simply shift that 14 bits to the right, shifting in zeros on the left, right? Then you go to the upper 32 bits and you shift that one, 32 minus 14, to the left, the other way, right? Which is 18. You shift that 18 bits to the left, right? Which shifts in zeros on the right-hand side. So after you do this, you're going to have 14 zeros on the right-hand side of this guy, and you're going to have 14 zeros on the left-hand side of this guy, right? So then what you do is you just merge them together with an OR instruction. You just combine them, right? So you shift the right-hand side 14 bits to the left, which is that was the original goal, was to go 14 bits to the left. But in order to simulate the crossing of the boundary, the upper bits crossing down into the lower register, in order to simulate that, you have to shift that one 18 bits to the left and combine them together, right? So that's going to take 3 instructions to do that. 3 instructions, a shift left, a shift right, and an OR instruction. OR, remember, is a bitwise OR instruction, right? Okay? Now, problem is you have to be careful about your register allocation when you do that, right? So make sure you keep track of what register is holding what value when you do that. That's the tricky part. Okay, so what about the square root algorithm? There's a lot of ways to calculate square root. The best way, I think, is Newton's method. It takes like 4 iterations and you get enough accuracy. But that one's tricky. There's also something called Cordic. There's a lot of algorithms. In fact, I think RISC-V actually has a square root instruction, but it's in the floating point instructions, not in the integer instructions. So we don't get it. They don't have an integer square root. That's just something weird that we're doing, right? So the easiest way to do this is through what's called a binary search. And essentially what you're doing here is you're finding the root of an equation in which the answer, you're finding the root of the equation x squared minus s, where s is the input value and x is the square root, right? Because if x is the square root of s and you square x and you subtract s, you ought to get 0, right? And so that's like finding the root of an equation, right? You're finding x is the root, right? What value of x will make x squared minus s 0? How do you do that? Well, you guess on x. You make a guess, And if the guess is too low, you increase it. And if it's too high, you decrease it. And then you repeat. Right? That's basically all you have to do. Except the amount that you increase or decrease is adjusted exponentially, or I should say logarithmically. Right? So what you have is you have a step size. The step size has to be adjusted to whatever is half the dynamic range of x. So whatever the range of x is, your step has to be half of that, right? But then every time you make a step, you divide that step by 2, right? And then you just keep going until your step becomes 0 because you run out of bits, right? So here's an example. So if I start at 0 and let's say that I'm going to set my step to 2, meaning that I expect the answer to be between 0 and 4, right? If the answer is going to be between 0 and 4, I'll set my step to 2. My first guess will be 0. So if I take 0 and I want to calculate the square root of 2, so I set s to 2, I square 0, I get 0. And obviously 0 is too low because 0 is less than 2. So I add the step. So now I'm at 2 and I square that and I get 4, but now I'm too high because 4 is higher than 2. So now I have to subtract. Now this time I'm going to subtract half the original step, which is 1. That gets me down to 1. I square 1, I get 1. Up, too low. I have to add 0.5. Now I have 1.5. I square that, I get 2.25. Too high. I overshot. So then I subtract 0.25. So now I'm at 1.25. I square that, I get 1.5625. That is too low. I'm trying to get to 2 here. So then I add 0.125. I get to 1.375. And I just keep repeating that until I eventually either run out of step, in which case that's the closest I can get to the square root, or I nail it. I get a correct answer, in which case I have to bail out, because if you keep going, you're gonna lose the right answer, right? Okay, so that's the algorithm, and that's kind of, I wrote it out there. Okay, so for the I put this binary search spreadsheet on Dropbox where I basically implemented this algorithm in Excel. The problem is you have to, like, say save link. It's weird about saving Excel files for some reason. You have to right click and say save as, and then you have to allow it to download here in Chrome. And then you have this binary. So this is useful for debugging. So it's a little probably more complicated than it needs to be. We keep tweaking this. So at the top here, it allows you to put in the number of fractional bits and then the input, right? So I'm going to use 14 fractional bits and my input is 25. Obviously, the answer there is 5. And so this keeps track of the iteration, the guess. Okay, wait, before I get to that, let me go to the lab sheet. I've got ahead of myself a little bit here. Okay, so if you open the lab sheet, which is over here under lab 1, and I opened it already here. Okay, so the goal is to write this code in assembly and test it in RARs. The reason we're doing this is because we're going to use this as our test program for lab 4. And it's going to give us, it's actually going to allow us to have the FPGA calculate the square roots, and we can input them on the switches and the output to the hex displays, and it looks kind of cool. It's basic, but it's impressive when you think about the fact that you built it from scratch. So this program is 50 to 100 instructions. It's short. It's just tricky because of the reasons I mentioned earlier, all the annoyances of assembly language programming. So in this case, we don't have a board yet. We just have RARs. So we're going to put the number in as a 3214 fixed point, but we're going to type it in as an integer, right? So basically, you have this concept now of input actual, which is the number that you intended to put in. So say 5, right? But when you type it into RARs, you have to type it in as a fixed point number, which means that you have to scale it by 2 to the 14th power. So you have to type in not 5, which is your intended input, but 5 times 16,384, right? Whatever that is, right? So that's called input raw, right? So we have this concept of input actual and input raw. Input actual is the number you want to calculate the square root of. Input raw is what you have to type in. Now here's the other problem. If you type in any number that's above 2 to the 18th power, then that means that the most significant bit of that number, after having been multiplied by 2 to the 14th power, right, you're going to end up with a number with a leading 1 bit, which is unfortunately a signed bit in RARS. RARS doesn't allow you to input an unsigned number. It only allows you to input a signed number. So in order to get around that, you have to do this other thing where if you want to put a big number in, you have to put in the negative complement of it, which is kind of confusing, I know, but this will make more sense once we implement this on the actual FPGA board with the switches. Okay, so I put the rules in here. Basically, the input raw is simply the input actual times 2 to the 14th power, right? Unless the input actual is greater than 131,072, in which case you do the same thing, but you just subtract it from 2 to the 32nd and negate it, right? So it's kind of an encoding thing you have to do. You have to basically take the number you want to put in and encode it, right? Okay, so I gave some examples there, and I even gave you the test vectors here. By the way, now I actually haven't tried. This is going to confuse the heck out of ChatGPT, I think. I haven't tried to put this in, but this is wildly confusing. But so the idea is that if I put in 16,384 as a raw value, that means 1 in fixed point, because that's the scaling factor, right? Is 1 over 16,384 is a scaling factor, right? 2 to the negative 14th power. So if I put in 16,384, the square root of that is 16,384 because it's doing a square root in fixed point. If I put in 0, then I should get 0. And then if I put in, for example, 409,600, that actually represents 25. And so I should get 5. And then, of course, the output there will be 81,920, right? So these are the actual test cases that I used to grade, or that I used to use to grade. I'll probably add some more this time around, now that I gave them out. And then there's some negative numbers here, like if you put in -1, -1 is all ones. And so this is actually the largest number that you can put in a highest magnitude number you could put in as an unsigned 3214 number, which is actually is 511.99988, and the square, I'm sorry, no, sorry, it's actually 263,143.99999, right? And when you take the square root of that, it's 511, and then of course that's the encoded version. Does that make sense? So I know it's a little confusing, but this is intended to be used to, once you get to lab 4, we'll just put this on the FPGA and we could test your CPU with it. Okay? Now, let's see. Let's see. Any questions about that? Is that clear? Okay, so the intent of this spreadsheet then is this is a great way to debug your code in RARS. Now, you guys know how to debug, right? You set a breakpoint, and then you step instruction by instruction. You can see what's going on in the registers. And so these values are going to show you how the register should evolve. So if we start out at 0, and we set our step to be 256, because the answer, basically the number we're putting in is, the biggest number is 2 to the 18th. And the square root of 2 to the 18th is 2 to the 9th, 512, right? So we're putting in a number, the biggest number we're going to get out is 512, right? So 256 is our step. But it's not actually 256. It's actually going to end up being 4,194,384. And so this just will track exactly how the numbers evolve in terms of which way you should be going up or down. So you're going to, basically, you're going to have a register with your guess, right? It's going to be 0, and then you're going to see it go up and down as it converges on the answer to the square root, right? And so you'll be able to simulate that in RARS, right? Now, how do you run RARS? So RARS, I've got it on a download here, but basically, to run it in the lab, you just type Java. public, I think I've got it in my, yeah, I've got it in my web directory. So if you type java jar rars.jar, it should open up. And there it is. Yeah, so it looks like this. And there's your editor here and your simulator here. And you can see the registers over here. And notice that they have names here, A0, S1, and so forth. And then they have the numbers over here, right? And then the values are here, and those values are in hex, but you can change them to decimal. I think I even put hex on that spreadsheet too, but I think it might be easier to look at them in decimal. There you go. So now they're in decimal, right, instead of hexadecimal. So you can control that. And I was going to demo this. I ran out of time though. But if you go to the help menu and you go to syscalls, the syscalls, this little document has all the list of the syscalls. It tells you how to read something from the console and to output it. Okay, but read the lab sheet carefully. Don't print a prompt because we're going to use like an auto grader for this, and it'll get confused. Just have a read and then print. Read input, print output. Right, that's it. Right, make it auto grader friendly. Okay. Also, you don't have to use binary. Like if you guys are figuring like, well, binary search is like so amateurish. You don't have to use that algorithm, but our partial credit rubric is based on binary search. So if you don't use binary search, if you want to go crazy and use another numerical method, you're welcome to do that, but it's pretty much going to be all or nothing in terms of the grading, right? Because we won't have a way to do partial credit, because the partial credit stuff is, you see the rubric is on the lab sheet. It's all based on that algorithm that I presented to you, okay? So just keep that in mind. Okay? Sound good? All right, we'll see you in lab on Wednesday then.